Hello viewers, welcome to the lecture series on computer networks. My name is Jasir, Assistant Professor, Department of Computer Applications, MES College Marampalli. In today's lecture, we are discussing network layer logical addressing. We know that to be able to participate in a network, each of the participating systems have a unique and universal way to access it. While physical address performs this duty in the scope of a local area network, it is the logical address that performs this duty in the scope of Internet. In TCP/IP protocol suite, two versions of Internet protocol addresses or IP addresses are used for this purpose: IPv4 and IPv6. An IPv4 address is a 32-bit address that uniquely and universally defines the connection of a device to the internet. The device could be a computer or a router. Topics discussed in this section are address space, notations, classful addressing, classless addressing, and network address translation. An IPv4 address is 32 bits long. They are unique and universal, which means no two participating systems will have the same IP address at the same point of time. The address space of IPv4 is 2 raised to 32. They are normally represented using a special notation called dotted decimal notation. As you can see in this example, the 32 bits are grouped into 4 bytes and the equivalent decimal number of the 4 bytes are substituted, which are then separated by dots. For example, just look at this two binary notation address given above, A and B. They are grouped into different bytes, 4 bytes, and then substituted with the equivalent decimal number. In order to create the dotted decimal notation, we replace each group of 8 bits with its equivalent decimal number and add dots to separate them. In classful addressing, the address space is divided into 5 classes: A, B, C, D, and E. In class A addressing, the last bit or the most significant bit of the first byte, as you can see in the figure, is fixed to 0, which means a class A address will have the first byte from 0 to 127 only. For class B address, it is fixed to 10, which means a class B address must be having the first byte from 128 to 191. Similarly, class C is fixed with 110 and class D is fixed with 1110 and class E is fixed with 111 and 1. Another thing to note in classful addressing is that in class A addressing, the first byte refers to the network ID of the address and the remaining 3 bytes are host IDs, which means, in other words, class A can have a maximum of 128 networks. 128 networks from 0 to 127, and each of these networks will have 2 raised to 24 participating systems in it. Similarly, class B is reserved 2 bytes for network address and 2 bytes for host address, which means it can have 2 raised to 16 participating systems in each of the networks. This is the number of blocks and block size in classful IPv4 addressing. Class A will have 128 blocks, or in other words, it can have 128 networks, different networks. Each of the networks will have one 216 computers that can participate in it. Whereas class B will have 16,384 networks, whereas each of the network will have 65,536 computers participating in it. In classful addressing, as you can see, a large part of the available addresses are wasted. You know that a class A address, which can have only 128 different networks, but each of the networks can have 2 raised to 24 participants in it. You can easily imagine that most of the largest, even the largest multinational companies won't be needing that much IP addresses. And these are the default masks for classful addressing. Class A addresses will have a default mask of 8 ones followed by 24 zeros. Class B will have 16 ones followed by 16 zeros, and class C will have 24 ones followed by 8 zeros. Or in classless interdomain routing notation, they are represented as /8, /16, and /24. These network masks are used in routers to add a particular incoming IP address and find out the network address. The topic will be covered in detail when we discuss routing. Classful addressing is now almost obsolete, which is replaced by classless addressing. Now, in classless addressing, a block of 16 or 32 or 64, basically a block of addresses which can be expressed as a power of 2, is granted to a small organization with its corresponding network mask. In the given example, the first address is 205.16.37.32 and the last address is 205.16.37.47. In IPv4 addressing, a block of addresses can be defined as x.y.z.t/n, whereas x.y.z.t defines one of the addresses and the /n defines the mask. The first address in the block can be found by setting the rightmost 32 minus n bits into zeros. For example, a block of addresses is granted to a small organization. One of the address is 205.16.37.39 and the mask is /28. What is the first address in the block? To find out that, let's take the binary representation of the given address, which is shown in blue color in the slide. And if we set the 32 minus 28 rightmost bits to 0, we get 100, 1100, etc. up to 0010000, which is 205.16.37.32. Similarly, the last address in the block can be found by setting the rightmost 32 minus n bits to ones. For example, the binary representation of the given address will be 205.16.37.47. The number of addresses in a given block can be found by using the formula 2 raised to 32 minus n. For example, if the value of n is 28, then the number of addresses will be equal to 2 raised to 32 minus 28 or 16. The first address can be found by ANDing the given address with the mask. ANDing here is done bit by bit. The result of ANDing two bits is 1 if both bits are ones, and the result is 0 otherwise. So when you AND a given IP address with the network mask, you always get the first address of the block. Similarly, the last address of the block can be found by ORing the IP address with the complement of the mask. ORing the IP address with the complement of the mask. The number of addresses can be found by complementing the mask, then adding 1 to it. For example, in our given example, the mask was having /28. The complement is all the 28 ones will be flipped to zeros followed by 4 ones, which is equal to 15 in decimal, and adding 1 to it, that is equal to 16. Usually the first address in the block is not assigned to any device. It is used as the network address that represents the organization to the rest of the world. There are many levels of hierarchies in IPv4. There will be an area code, then exchange code, and then there will be a subscriber code as well. And the 28 bits are used to find out the network prefix, whereas the last 4 bits is reserved to the host address. Each address in the block can be considered as a two-level hierarchical structure. The leftmost n bits define the network. The rightmost 32 minus n bits define the host. Here, a network that consists of 64 computers are shown in this figure, whereas these 64 computers are divided into 3 subnets. The first subnet is having 32 computers in it. The second subnet is having 16, and third subnet is also having 16. The idea is to get a block that consists of 64 computers with a mask /26, and then divide it into 3 different subnets with masks of /27 and /28 respectively. This idea is known as subnetting. Similarly, when you get more than one blocks and merge them into one, it is called supernetting. IPv6 addresses. Despite all the short-term solutions, address depletion is still a long-term problem for the internet. For this reason, IP protocol itself have been the motivation for IPv6. Here we discuss structure and address space in this topic. The IPv6 address is 128 bits long. As you can see, the 128 bits can be represented using hexadecimal colon notation. The hexadecimal colon notation can be abbreviated by skipping contiguous blocks of zeros by just mentioning 10, or it can be more abbreviated by entirely skipping the contiguous sequence of zeros. In this lecture, we discuss IPv4 and IPv6 addresses, their structure, their representation, classful addressing, subnetting, and supernetting. In the next episode, we will discuss